There are now more mobile devices on the planet than humans.
What we have to remind people is that every time they touch their iPhone or Samsung or whatever brand you carry in your hand, you are using mined products.
And demand for new technologies isn't going away.
As we try to generate more and more of our electricity from renewable sources, as we shift over to using electrical cars, we have to find new resources.
But with the Earth facing unprecedented human pressures, how do we get it right?
It's going to be really important for us to develop our green technologies, and that's why we need a much more rounded understanding of what we're looking at.
SoS MinErals is at the heart of understanding.
SoS MinErals stands for the security of supply of minerals.
Minerals that are really important for high-tech applications.
Tellurium and selenium, critical components in photovoltaic cells, so solar cells.
Tellurium is really important for the future.
It's very positive for science to have a greater understanding of these minerals.
Cobalt, this is used in batteries for electronics.
No cobalt, no Tesla.
SoS MinErals is really another way of thinking about how we can access mineral resources.
Dysprosium is a rare earth element.
Rare earths used in wind turbines and electric vehicles and hybrid cars.
SoS MinErals has the potential at least to untap a whole new host of technologies for the future.
Neodymium, it increases the strength of iron-based magnets.
We're changing the parameters that we would use to determine what is a resource and what isn't, providing information for society to make a choice about resources.
It's a win-win.
In the laboratory and in the field.
Seeing the end game for your science is so very, very important.
Across the sciences.
We've got biologists,
communities working together,
physicists.
Everybody brings all these different skill sets to the table.
Chemists.
We're not isolated.
In addition to the geologists that we normally would expect.
Securing solutions for all our futures.
It's just a fantastic opportunity.
Something that actually should make a real difference.
Oxfordshire, home of one of the UK's major science centres, Diamond Light.
Diamond's a synchrotron. 3 accelerators, all working in tandem. We accelerate electrons, we can look at cells, we can look at engineering particles.
Today, there's a briefing for some visitors.
We are looking at samples that are down to 1 micron by 1 micron.
We brought our cohort of 19 PhD students, a very diverse group of young people who are completely engaged with the SoS project, and we brought them together to really get them to look at things outside their own science areas, really bond as a group.
"19 young minds representing all the major science disciplines.
Camilla Owens, University of Exeter.
Andrew Martin from Cardiff University.
Saul Mulroy, University of Manchester.
Robert Pell, I'm from Camborne School of Mines.
We are bringing on these biologists and fundamental scientists, physicists and chemists who are giving us that sort of step change that we need.
Looking at recovery of a rare earth ore from a mixed synthesite apatite ore.
Looking at bioextraction of cobalt from iron and manganese ore deposits.
These people are going to form the backbone of the next generation of scientists that are going to be working in the natural resources area.
My PhD is in responsible sourcing of rare earths.
Distribution and enrichment of tellurium and selenium in volcanogenic massive sulfide deposits. You very rarely get so much collaboration between different disciplines.
Looking at the same problem but from different aspects.
So it's really complementary, all the research.
It's actually really awesome.
All working towards the same goal.
The diamond machine is kept at 22 degrees, plus or minus half a degree. Temperature stability is very important. One you don't want
diversity of discipline, but unity of purpose. What defines the students also stands for everything that is SoS MinErals.
SoS MinErals is a research project that's been funded to look at these speciality metals.
For building solar panels and for building batteries and for building electrical components.
The raw materials that are needed for the products of modern technological life.
Rare earth elements, cobalt.
As the population increases, we're going to have an increased energy requirement, and we want to be able to supply that requirement using green energy.
Selenium and tellurium.
We reduce the cost and we reduce the limit on how many of these things can be produced, how expensive they are to produce, and how much energy can be produced and stored using them.
But mineral extraction has to exist in the real world.
General problem, suddenly they've become under great demand. In the case of one group of elements, the rare earths, they are produced almost exclusively in China.
More than 50% of the world's cobalt comes from Central Africa.
There's been quite a lot in the media recently about conflict minerals and child labour being used to mine cobalt deposits.
It can be a problem if you get your resources from a limited market by a limited supplier.
There should be a lower impact to mining these resources. They should be very widespread, so a much more global distribution of the resources.
At a cost that we can afford, and I mean that economically, environmentally and socially.
Security of supply is the goal. 4 linked projects are the method. COG3 for cobalt. Technology and biology combine for cleaner, safer, more ethical extraction.
We really need to understand much more about, why it's there, how it's there, and how biology might allow us to get at the cobalt better.
T's for tellurium and selenium, without costing the Earth.
How they're enriched, why they're enriched, and where they're enriched, so that in the future we can then mine them more efficiently.
SoS Rare, scouring the planet for safer sourcing of rare earths.
For future deposits around the world, we can select the right ones which are going to have the minimal environmental issues.
And under the sea, Marine E-Tech unravels mineral and biological ties to unlock resources for green, sustainable technologies.
Create a much more rounded picture of the seafloor and a much more rounded understanding of what we're looking at.
And throughout, the pooling of expertise across the disciplines is bringing true scientific innovation.
What we have here is a rock type from North Wales. It contains an energy resource that some microorganisms can utilise. My involvement is to look at ways in which we can use microorganisms to extract cobalt from ores and develop a green biomining technology in place of the traditional technologies. Once the bacteria have done, what you can see is that there are large holes or pits in the rock. And these pits are where the sulfide minerals used to be. So they digest out what they can use and leave the undigestible residues behind. And the digestible parts contain the metals that we're after.
When we go out with the ship, we take a whole load of different bits of marine technology with us. So we look through the top few tens of metres of the seafloor. And my job as a postdoc on this project is to interpret that data. We have some X-ray computer tomography, super high, like nanometer resolution, 3D images of some of our samples. And if we're able to derive a lot of information about the seafloor without having to collect any samples, without having to disturb anything, and it gives us a really quite quick and accurate way of assessing a potential deposit on the seafloor.
Just 2 of many research innovations, and all under a programme that's very definitely facing outwards.
Working with industry throughout has been a key part of the programme. There's no point us doing the most detailed work in the world unless we're actually feeding directly into generating information that's going to benefit society and industry in producing these things.
So geologists to find new sources of the minerals, chemists and process engineers to find ways to extract the minerals, and then look to the particular devices and say, what is it you really need for your battery? Do you want it as a liquid or a salt? So we can then tailor these extraction processes.
Okay, can we head upstairs now? That's fine.
The tour of Diamond Light is finishing.
Okay, come on everyone, please.
Soon, the students' work will be too, as SoS MinErals enters its final stages. So what will be its legacy?
When SoS MinErals finishes, there will be the groundwork done for moving on.
As SoS MinErals is coming to an end, we need another one.
The son or daughter of the NERC SoS programme.
We're just sort of, looking over the first few pages of what needs to be done to ensure that we get a responsible supply chain of these critical metals.
We've always got questions we want to answer.
I think it's really important for us to continue to fund projects that are like this, like multidisciplinary projects.
I hope that the project has a life of its own afterwards, maybe through industrial links that have been generated through these fundamental studies.
We're already in talks with companies, with organisations. There's a lot of excitement.
The opportunity to train scientists, but also to include the involvement of companies and corporations.
For the UK, this is going to underpin our development in the future.
I think the key outcome at the end of the day is that the UK retains and develops excellence in science in these fields.
The UK really needs to stand alone now and show that it still has interest in this kind of area of science, so even more important.
I'm very hopeful that we will continue our relationship with European scientists. And maybe we could use this opportunity to remind ourselves that there is the rest of the world out there.
We need to keep it internationally focused. We need to be working with other countries and we need to be looking at a global supply chain.
Mineral technology is very international. We have to be at the forefront of this.